You have fallen into Event Horizon with John Michael Godier. In today's early release, John discusses breaking news on the Wow signal with Professor Abel Mendez. Professor Abel Mendez is a planetary astrobiologist and director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. His research focuses on the habitability of Earth, the solar system, and extrasolar planets. He is a NASA Mears Fellow and has also conducted research at Fermilab, NASA Goddard, NASA Ames, and the Arecibo Observatory. We'll return to the regular schedule next week.
Professor Abel Mendez, welcome to the program.
Hi, hello. My pleasure to be here.
Now, Professor, you have a paper out that literally made me exclaim, wow, when I read it, because it's about the wow signal. And what you have here is the first, in 50 years, the first compelling natural explanation for the wow signal that it checks all the boxes right down the board. And there's one in particular that I'm interested in. And I think we'll start there. So this is a little known fact about wow, but Bob Gray, who had a huge interest in the wow signal, recently passed away. Well, he wrote a book on it, and in that book he noted that in his observations, the apparent blue shift, there was a slight blue shift or what may have been blue shift in that signal. And he said it matched the hydrogen clouds in the background of that area. And I thought, well, if this paper is correct and it was a flash of those hydrogen clouds, that would be consistent with that discovery. And that really piqued my interest. Now, could you give us an overview of your idea of what the wow signal might have been?
Well, this has been a lot of work since May. We are trying to create a new project, a side project of our Arecibo data that we has been taking from 2017. And so we started this new side project to look for wow signals during this summer. And then we saw one of the similar signals, but we immediately recognized the signal due to atomic clouds. Very cold atomic clouds. Atomic clouds in the galactic hydrogen, they emit narrow band signals if they are clouds, if they are cold. Usually there are so many at different temperatures. That's why it's a broadband signal of many components. But if these clouds are small enough, they will have a narrow band frequency. And I saw those, and when I saw those, I thought at the moment, okay, this is the clouds, but this is so similar to the wow signal that the only difference for them is to be brighter for a moment, and that will perfectly match. So then I look for different options of how these clouds could become brighter. There are many options. For example, even a supernova compression of that hydrogen gas will allow this cloud to emit in the hydrogen line. But because the gas is compressed and it will be moving, this signal will be broadband and will be recognized as something astronomical. So the only option for make these clouds brighter and still keeping the same temperature, the same narrow band, is a stimulate emission. So we think it was another event, like a magnetar flare, which emits a lot of energy in all bands, but including radio. So these magnetars will emit a strong radiation toward Earth. And if you happen to have that cloud with that density, which is already a little bit brighter than the background, and it's cold, then you will make it excite the atoms there and create a temporary maser-like effect, a maser flare. So that's what we think the wow signal was.
So essentially, it's an amplification of a background object. Like, as you say, a magnetar. Let's use a magnetar as an example here. Well, it's a highly magnetized neutron star. It's an environment that could create a signal for sure. And
Yes.
it's just filtering through in just such a way that the clouds just got excited. And the normal 1420 emissions of the cloud became much, much greater, but for a very short period of time, which would explain why WOW was so transient and didn't get picked up by both feed horns of that radio telescope, right?
That's true. And the thing is that these emissions from the magnetars will be broadband. So it will emit in all frequencies. And you might think, okay, so why we don't saw through the WAP signal all frequency? Well, it could be, there are two ways that could make the original source invisible to your detection. Is that it could be not intense enough for your telescope, but because inside the clouds, when these emissions are amplified much more than the original signal. So you just see the original signal, the signal from the cloud, but never the original signal, which more or less will be concise in time. And also the second option is that there could be a delay, a little delay, probably seconds, minutes, or hours between the signal from the magnetar and then the maximum brightness of these clouds. Is that so? Then, if you are having the telescope like Big Ear scanning the sky, you miss the because of timing the magnetar output, but saw the brightness of the cloud.
In other words, an echo. And you just have this excitation.
Yes. It's a kind of echo. Yes.
A kind of echo. But it also reminds me of a lightning flash in a cloud, in a storm at night, where you see it, and then you're just waiting for the next flash, which you have no idea when that's going to be. And I guess that's the case here, in that there's nothing predictable about whether this magnetar can do this, or if anything is aligned. No wonder no one ever saw that signal again, right?
Yes. John, that's exactly how I put it also in my mind, like a lightning in the clouds.
Well, there's a beauty to it, because what this tells us ultimately is that, yes, the signal was real. This was a real astrophysical signal, and that the scientists involved that discovered it at the Ohio State University with the Big Ear did not make a mistake. This was an unknown. Their problem was they didn't know this could happen back in 1977. And indeed, maybe 5 years ago, we didn't know this could happen. But there it is. And it actually really is intriguing, because the more we find out about magnetars and their environment, the weirder they get. These sort of extreme environments, and how they affect other things, including a hydrogen cloud in the interstellar medium, to excite it this way. And if it's small enough, it can do it narrowband. And it's just very amazing. But what is the luck of having actually just saw that randomly?
Yeah. And actually, also to see these clouds, even that they're detectable, they're bright, but definitely their current brightness is not enough. It was not enough for Big Ear, for the sensitivity. They are not that bright. You need a big telescope. So that's why we saw those clouds in Arecibo. But even so, it also depends on how you analyze your data. I recognize the signals because I was looking for them in the data, and I took the time to create a code which I learned from the original WOW signal, how they did it, how it was analyzed. So I was trying to mimic every step of the analysis that they were doing, plus adding modern versions of just for comparison purposes. And otherwise, these are things that you're not looking for in particular, because if astronomers that are looking for measuring these atomic clouds in the galactic plane, they usually integrate all frequencies, because they just want to learn how much hydrogen is in the field of view. And when you do integrate everything, because you have a lot of data and you have to reduce that integration, you just see the total output of that, and you don't see at any particular frequency. You're doing this because you need to, when you integrate, you improve your signal to noise ratio. but you will miss that. So that was something that I was doing, and I didn't see that in my previous analysis. And when you are looking for spectral lines, and in this case you are looking for particular frequencies, but you are integrating in time because you again want to increase the signal to noise ratio for detection. You are integrating everything on time, and if you have one signal that is strong but it's a short time, you will miss it. So that's again, I was missing everything from what we learned this summer from my previous data, because I was using more standard procedures in astronomy for detecting different things. But once you try to look for a frequency, and the other look, it was the telescope. The sensitivity makes everything easier to find.
Yeah, well, the Big Ear telescope was, I mean, that was 1977, and it was already essentially a retired telescope after mapping the hydrogen clouds of the Milky Way.
Mm-hmm.
And the receiver that it had back in those days, it's 50-year-old technology. And as a matter of fact, I think the WOW signal, there was only 50 channels, which now, what's SETI search now? What future do you see in looking for signals using this sort of temporal method where you're looking at much shorter timescales? Yeah, I mean, do you see that as the future of SETI when, looking for alien signals? Do you see room that they could be hidden in there?
Well, there's a big issue here because now we have a search for false positive. People in SETI has been looking next to the narrowband signal close to the hydrogen line, because probably extraterrestrial civilizations will use that as a communication frequency. But now that we have that, we can have false positive astronomical phenomena in that region. That means everything harder to differentiate. Because if you look back at and this is what I was doing through the analysis, when I learned in detail the timing, the intensity of the original WOW signal, that everything was telling me this is a hydrogen maser, and hydrogen masers are made artificially, and it's believed that this type of hydrogen in the lab, these hydrogen masers are difficult to make in the space, astronomical hydrogen maser. There are many masers in space, but due to other species like OH or so, other molecular species. But for hydrogen to be a maser, that's very hard. And there's no very hard. So I think that's the big deal here in our proposal for the origin. That it's not only that is these small clouds that we know are common, not that easy to detect, but they are common. But also this maser flare to be produced, that's something that never seen before. Plus the alignment, and that's it. So there are many conditions here that makes everything harder. But it seems to be possible. But now that we know that this is a strong possibility, there are two ways that we can move forward. One is we can look at archive data, like just exactly what I did. We had those observations in 2020 from the Arecibo Observatory. They were in early 2020. The collapse of the telescope was in late 2020, in December. So we can look through archive data. And I think that's the most promising venue, because there's a lot of data that you can analyze. And even the Arecibo data is already there. You can analyze and look at it in this way. But also for people to look for new data. And one thing that we are proposing, and I'm very excited about this possibility, is assuming this hypothesis is correct, then it means that for this to happen, you need a cloud, a small hydrogen cloud. And those are easy to detect if you have the right telescope. So we don't know where exactly, we know the regions where the WOW signal came, but we don't know exactly what particular region starts. That people have been arguing, thinking about the exact location. But if you map those areas with the right resolution and the right analysis, then you can pinpoint this cloud, which I expect won't be that many, maybe let's say 6, 10. So that means that the actual source will be behind on one of those clouds. Well, the source, the magnetar, may be something that you cannot detect it, but now that detected before, but now that you have a spot, you can look through other telescopes to look like interaction with the background stars with a object that you don't see, because magnetar emit this strong radiation source, but they usually does that in one particular direction. It's not always going all the way in all directions. So maybe you don't detect, or maybe it's not as strong to be detected, but you can maybe it's orbiting an object, and you can detect the interaction of gravity with that object and say, that mass corresponds to something very dense that I don't see. That may be some small object like a magnetar orbiting that. So this will be something great for me to do, and something that we want to do also, just to look through the original wild signal and map potential candidates. And the other thing is that people might be interested in looking to other regions, other of this cloud. But what's the chance that if you pick a cloud of this type in other parts of the sky, you will have the right objects emitting at that moment? Well, you will have to wait a long time for that to happen.
And I'll bet you it's even more conditional than that when you get into looking at the hydrogen cloud. I imagine it needs to be a certain volume or whatever that could, change equations and make this a very, very situational, extremely rare event.
Yes.
But yet, you did see those other signals. Now, what were they? The other similar WOW signals that you were able to attribute to molecular clouds. What led you to believe those signals were specifically due to being gas?
Because I see them at different targets. They definitely look like the WOW signal, but they are constant in time. They're always there. So I look different regions. I see those in different regions. I have multiple scans of the same region, and they are consistent. They appear every time we measure, different days. So it's pretty clear, and that when you take the bandwidth of that signal, which was 10 kilohertz, so the same frequency that what signal was detected in terms of the bandwidth. So, and you calculate from what temperature you will need a hydrogen cloud to be at that temperature, and you get 100 Kelvin or less, which is exactly what you expect for the hydrogen cloud.
So, next question. All right, Arecibo. What are the projects going on now with your laboratory at the University of Puerto Rico?
Well, so we will continue our original project that we started in 2017, looking at stars with planets. We were studying the activity of those stars or the space weather, because that could affect the habitability of those planets. So this is a stellar habitability project. I never thought that I will move to a techno-signature project, research for life project, but using the same data. But we'll continue analyzing that data. We have some interesting events in that data regarding on particular stars that we think they're too irradiating the space around the stars for the planets to have any atmosphere at all. So probably some more bad news about alien life in one of those potentially habitable planets. And so we will continue the analysis. We are requesting now more time in other telescope to follow up a few of our targets and continue that project. And meanwhile, we started this Arecibo Wow project this summer, and this is what the paper is about. At the beginning, we were not thinking about finding anything of interest in particular. I was thinking more like, okay, through this project, because the likelihood of detecting something, I think, is. But we have to look. The thing is, even if we think that the chances are very low to detecting anything, not because there's no possibility of aliens, and I mean because of the chances of the distance, sensitivity, the timing. There are many things to be aligned to have a detection. But anyway, we have to look, and one particular thing of interest in our data is that we were looking at objects of interest. We were looking at stars with potential habitable planets. And when you're looking with radio telescope, the beam size or the area the field of view that you have, you are getting all the signal from that region. And it means the stars, the planets, and some background stars and some stars in the side. So you're getting a lot of information there. So if anything is transmitting in that direction, you will get it, depending on your sensitivity or your telescope. So we thought that through this project, I will get a paper in 1 year or 2 years, addressing that we look at these stars and we have this sensitivity and we didn't detect anything in that region for this timing, for this sensitivity, and in these frequencies. And that's it. We know something. So it means, and this null result, you say, why is that null result is important? Because other people will see that null result and they say, well, let's look in that star. Oh, but these people look in that star and that frequency, that sensitivity. We need to improve that if we want to detect something. We still believe that there is something, but it was not detected. So that's important to have this on record for others to continue improving what others have been doing for searches. So that was what I was thinking was the destiny of this project, and not having the surprise this summer of having these signals and connection immediately with the well signal. But we will continue. We will continue with this analysis of our data, and once we finish with our data, then we will move to all archive Arecibo data. That data is already safe and available for scientists, and we will look through these methods to get all that data. So it will take a long time. So the Arecibo data has been saved since in the 60s. So we will have a lot of fun looking through that.
That must be a huge mountain of data for that
Yes.
telescope. That much accumulation time, and it was online though most of the time. So
Yes.
now, characterizing stars as far as habitability goes brings us to the question of red dwarfs, which obviously are popular targets to look at. And the problem is that they seem to be very noisy stars, flare stars, at least when they're young.
Mm-hmm.
What are you seeing so far as habitability regarding red dwarfs? Because they're the most common type of star in the universe. And we know that some of them have planets and all these sorts of things, and maybe there might be something there. But would you characterize yourself as hopeful, cautiously hopeful, that red dwarfs may be habitable? Or you say, I don't know if you can have an atmosphere around that, at least in the habitable zone?
Yes, that's a big and the most interesting question right now for astronomers studying red dwarf star. We are studying those stars, and people have been theorizing about positive things of red dwarf stars compared to sun-like stars like ours, or negative things, and probably is more negative things. But this in theory. But now that we have more observation, and I mean James Webb, for example, the TRAPPIST system, and other observation of the atmospheres of small planets around these stars, is shifting to really negative, more bad news for this. And we have observations also that I was mentioning you that haven't been published that we think is really bad. So every time I look at the actual data, what we know of these stars, which is not much, and the planets, which is not much either, it seems that habitability in these stars is really difficult. Probably the biggest difficulty is for the planets to keep an atmosphere. These stars are very active during the young phases of their formations, and the planets, and they keep being active through the lifetime, not that much. So it's not the problem that the strong radiation levels and the flare will kill immediately life on the planet. No, it's not that strong. But definitely in a million years, it will erode the atmosphere of this planet. So it will be very hard for these planets to keep an atmosphere. And that means it's not impossible, but you have a more special condition. For example, the planet could be formed farther away from the star. I mean, outside the habitable zone, it will have more water as ice. But then through migration, depending on how many planets you have in the system, it could migrate. So it just the planet was safe from the first billion years of the star activity, and then it moved to the habitable zone, and that much water will become an ocean then, and much of the atmosphere survive, and then the planet is now fine. So trying to invoke habitability conditions still possible, but probably they will be more rarer for the red dwarf star.
Now, what about Type K, the orange dwarfs?
Yeah, those are in the middle, and dwarf and the sun-like stars. K stars seems to be fine. So when astronomers say sun-like star, they mean G-type star like our sun, and K star type, which are a little bit smaller. So those are fine for no issue yet, as compared to N dwarf. So basically, there's some studies and theory have argued that probably some G types like our sun are better, or K type are better, which are more common than G types. But basically, they're in terms of properties, they are very similar stars.
And though they are more long-lived than G, generally speaking,
Yes.
so you've got that going for them, and then their habitable zone, of course, is quite a bit further out than a red dwarf. That was always what worried me, was that in a red dwarf system, that habitable zone is very tightly in there. Mm-hmm. And when we started doing the Webb observations of TRAPPIST-1, they started to see those first two planets. Nope, no atmospheres, and I was like, "Uh-oh,
yeah,
the red dwarfs are moving in a different direction now."
Yes,
but it's been an ebb and flow, because pessimism versus optimism back and forth regarding the red dwarfs. But it always seemed to me that the Ks didn't suffer from any of that, mm-hmm. and that you're in a much more sun-like mm-hmm. stage. Mm-hmm. And it's also worth noting too that sun-like stars, type G, not particularly rare. Mm-hmm. I mean, they're out there. So even without the red dwarfs, where it becomes very conditional for habitability, there's still a lot of possibilities to search, and even maybe type F, but then you're getting into really severe ultraviolet and things like that. Mm-hmm. But that's still a lot of stars to search. Now, I remember you were involved also with the Planetary Habitability Index, as I recall, correct?
Yes.
Current favorite Earth-like planet, which is the closest?
Well, okay, so we keep the Habitable Worlds catalog. It was previously called Habitable Exoplanet catalog, and we changed the name because we want to include moons and everything else. So it's Habitable Worlds catalog now, starting this year. And we keep track of those objects of interest based on what we know of them. So in particular interest for us is Teegarden star, which has two potentially habitable planets. And in terms of its size of the planet, well, we know the mass, but the mass we can estimate is high. It's more similar to Earth, and the position of one of those planets with respect to the insolation that it received from the star, but it's still a red dwarf star, then they are more similar. So you see here that this index is considering just those two parameters, and in those two parameters, Teegarden star, a red dwarf star, are a good candidate. But if we can say, well, okay, let's have the index only for sun-like stars, then you are in no luck, because we haven't found, for example, one of these planets in the habitable zone, Earth size, around a sun-like star, in a good position to have a similar flux to Earth. So most of the data is for red dwarf star, because the planets are easy to detect red dwarf stars. That's something that will be changed in the future with the Habitable Worlds Observatory, that it will be able to look through sun-like star, K star and sun-like star, and detect planets. Because with the other methods, with the transit methods, or especially the radial velocity method that are used to detect those planets, it is more harder. These methods depend on how much the planet affect or the visibility of the star through transit or the motion of the star through gravity. And because if the star is bigger, like K star and sun-like stars like G, so then that influence on the planet on the stars is difficult to detect, and that has been the issue. We have more knowledge about M-dwarf stars because the planets are easy to detect. That doesn't mean that those stars have planets of interest that we just need to discover. And so far around sun-like star, we need a good candidates.
So how do you look for the candidates? So as far as sun-like stars, I mean, do we even have a mapping of near? I know we're trying to do that with red dwarfs, but do we have sufficient? That's what the word I'll use. Sufficient mapping of sun-like stars near us to really do a complete survey.
Yes, and people have been looking through telescope for this star, but they are only able to detect the big planets. The planets are the Jupiter planets, Neptune-sized planets. Once you go into the super Earth or Earth-sized planets around these stars, and especially if the system is farther away, it's getting harder. And you need precise photometry for that and a long time of observation. And that's what the Kepler mission did, observing a patch of the sky. And most of those stars are far away, so are only detectable because they are bright stars, they are sun-like stars in the Kepler field. And he had this sensitivity for the small signal and the patience because if the planets are around this star, they are in the habitable zone, they will take a long time, a year, just to get another transit, 2 years for two, and so on. So that's why Kepler mission kept looking at the same patch for 3 years, just to get enough to make sure that those transits are not some random variation in the data, but also, but for sure, to a planet. So that's one way to do it. But if you that's good for exoplanet statistic of how many Earth-sized planet, about sun-like star, and so on. But we have some good candidates, but the candidates are so far away that you cannot characterize them anyway for the how much atmosphere they are. You just can't do that of the nearby ones. So the nearby one that you can detect like that are the red dwarf stars. So, and for the most of the Kepler candidates, you cannot characterize or follow up for what the atmosphere. You need nearby planets, and that's the big deal. But Habitable Worlds Observatory will look and we hope use a different method to detect planets. It will be imaging, so it will block the light from the star, and you will see which the brightness of the star will outshine any planet. So if you block the light of the star, then you might be able to see the planets at Venus orbit, and Earth orbit, Mars orbit, around this. And the planet could be in any configuration. It doesn't have to be edge on like in the transit methods or one particular condition. And also for the transit method, you don't know exactly what the orbit is. But so you estimate the minimum mass and not the actual mass. But here you will have all the information that you need, and you will have the actual light from the planet. And once you have the actual light of the planet, then you can do a spectroscopy and the emission spectroscopy, not absorption spectroscopy, but also emission spectroscopy, which will tell also of the components of the atmosphere. And that will be amazing. So that's definitely the big next step.
Yeah, and when is that going to happen? So what is the time frame?
So the Habitable World Observatory is approved and in plans now with NASA, and NASA made all the commitments so far. Things could change, but all the commitments so far, and the teams and the committees for designing the instrument. So this is a project that will be in 2030 something, for when we see the launch or results. Probably, if we are lucky, in late 2020s. But I think in practice, probably the best result will come in early 2030.
Not that far. Not that far
Not
off.
that far. Not that far. Not that far.
And yeah, you're right. It'll illuminate everything, much in the way as Kepler did, because Kepler, we should have manufactured about 50 of those and watched different parts of the sky. Because that thing just racked up thousands of transits. But it wasn't just that. There was data in there, if you've looked at the light curves, on variable stars, and weird stars like Tabby Star, doing something we don't quite understand, which that's another subject. But there was a lot of data there, and I'm like, wouldn't it be cheaper if we just manufactured like 50 of them instead of one? Just started launching them whenever we could.
Yeah.
What's your thoughts on that? Or is it? Yeah. Are we past those days? Can we do way better than that experiment now? I know we have tests, but anyway.
Yes, I think people think that we are spending enough in all this, but no, we need more telescopes. When we miss a telescope because it's not working anymore, or Arecibo collapse, that's a lot of information that we are losing. And as astronomers are struggling to propose different ideas, and they have to reject many of those ideas through the observation times, because there is not enough time to use all the telescope on our planet. We need more telescope. Yes, definitely.
Any chance of building a new telescope at Arecibo?
Well, Arecibo Observatory is moving through a new phase, and now will be called Arecibo C3. It's an educational project supported again by NSF, but it's only for education. And amazingly, it will be a totally different approach, because they will be focusing now in biology, education in biology, computational biology. And so those facilities are being rebuilt or adapted for this new purpose. The museum will be there as before, with different exhibitions, more in general STEM now than astronomy. And the observatory dish, the columns there, everything will be there for people to see what was left of the original observatory. And they have a museum exhibition, many of the artifacts from the original telescope. And they will have an inauguration on November. That's the plan. They will have a big inauguration of the new facility of the observatory. And we will have an activity, also a quite interesting activity. And regarding the wow signal, listening to message, also to sending message, the Arecibo message. Remember, the Arecibo message was sent from Arecibo in 1974. And that in November, we are celebrating the 50th anniversary of the Arecibo message. And we will have a lot of exhibitions, and people don't know yet that the Arecibo Observatory was planning a new message. They had a competition from 2018, 2019. The winner was selected in 2020 in the summer. And by August that 2020, the first cable broke. And they have other issues concerned about the observatory at that time, but they awarded, at least they let the student know that you were the winner for the competition to create a new message, a new Arecibo message. So the competition name was the New Arecibo Message. And the students were recognized internally, but what the student didn't know was that they were planning to send a message. That there was a surprise for the student, for a part of the prize to come to the observatory, but under the excuse that this is a VIP tour of the observatory, but we will send your message. That's a surprise for the students. So that was planned, informally between us at that time, and as a surprise for the student, but then the first cable, and then the collapse. So that never happens, and nobody in the world learned about that. But we want to change that. In November, we will take advantage of this celebration, and we will reveal what was the message. And now we call the last Arecibo message, the message that was never sent. So we will reveal that for the press. And the students will be there. And we hope through the whole month have a celebration of the legacy of the observatory, and the science, and the search for extraterrestrial intelligence, and even sending message. So that's what's going on.
Quite a lot still. quite a lot. All right, Professor Mendez, thank you for joining us today. It's always a pleasure, and I look forward to checking in with you again as your work progresses. And very exciting stuff about the WOW signal, because that was just so perplexing for so many years, and it didn't look like there was going to be a resolution in sight ever. And here we are. We've got something pretty compelling.
Yes, thank you very much. I was surprised too. We rushed for having this paper because we thought this is something quite interesting to put forward, because there will be ways to people to verify this and get new science.
I'm actually excited about this, because it didn't turn out to be interference after all. It was something. There was something there. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.